Alright, in this video we want to look at gravitational acceleration on a different planet. Now this also works for the surface of a moon or asteroid or comet or anything like that. So we get really used to using g equals 9.81 meters per second squared on the surface of the Earth, but this is very specific to the surface of the Earth. So these types of problems are good at reminding us that g is not universal. It depends on the mass and the distance you are away from the center of a planet or some other celestial body. So in this problem, let's look at how to find the gravitational acceleration somewhere else. So you're a scientist working on planet Q, and you want to find the acceleration due to gravity near the surface. So you climb onto a spacecraft and drop a rock from a height of 4.6 meters. It hits the ground 1.3 seconds later, and from that we can find g on this planet. And then we want to compare that to g on Earth. So let's get rid of this. And we'll look at what we have in this problem. So we're dropping a rock, and it's going to hit the ground. We know that the height that we're dropping it from is 4.6 meters. So that's our change in the y direction. And we know that t is equal to 1.3 seconds. So it takes 1.3 seconds for it to fall. And this delta y is actually negative because we're starting off from a higher point and ending at a lower point. So it's falling downwards. So delta y, y final minus y initial, is negative 4.6 meters. So all we have to do for this type of problem is just use our kinematic equations that have the height or distance and the time. So in our case, the best one to use would be delta y equals v initial times t plus 1/2 times the acceleration times t squared. Now, in this problem, we're told that the object is dropped. So anytime you see dropped, that means v initial equals 0 meters per second. It means they're not throwing it downward. So it has no initial velocity, and that makes our problem a little bit easier because we can just say v initial times t equals 0, and now our problem is just delta y equals 1/2 a t squared. So we just want to solve for the acceleration because this is our g for this planet. We'll call it gq. Solving for the acceleration, which equals g. We're just multiplying both sides of this equation by 2 and dividing by t squared. So that's 2 times delta y over t squared. And we're plugging in our values, so that's 2 times negative 4.6 meters divided by 1.3 seconds, and that's squared. And we have two significant figures in the values that were given, so we will say that this is 5.4 meters per second squared, or negative 5.4 meters per second squared. And this is the acceleration due to gravity on planet Q. So we can already see that this is a little more than half of 9.8 meters per second squared, but we're going to go ahead and give a more exact number for the comparison to g on Earth. So usually you'll see this in a lot of physics problems. It's just to let us kind of wrap our heads around how much bigger or how much smaller something is. So what we can do is use a ratio. So g on planet Q to g on Earth is going to equal negative 5.4 meters per second squared. Of course, it's negative. It's pulling toward the center of Earth on our planet as well, so that's 9.8, negative 9.8 meters per second squared. And this is going to give us 0.55. So this is saying that G on planet Q is 0.55 times G on planet Earth. So let's write that as GQ equals 0.55 times G on Earth, or a little bit over half. So this is our comparison. Now there are other ways to find the acceleration due to gravity on a different planet or other body if you have the mass of the planet and the radius of the planet, but we don't, and this is a type of problem that you'll see regularly. So we can use kinematics to find the gravitational acceleration by just dropping a rock. So hopefully that was helpful, and let me know if there's any other types of problems you'd like to see.